In this video, we're going to take a look at example number 3 and how we can use the calculator to help more quickly answer questions that require the use of Newton's method. Now, the process of using the calculator is all summarized here in this box, and I'm not going to read through this here, but I'll just kind of show you how to implement each of these individual steps as we try to answer a question here like number 3. Notice that this question is going to ask us to find, correct to 6 decimal places, a solution to the following equation. Okay, now a couple of things here are very, very different. First off, we should note that we don't have an equation that we're trying to make equal to 0. And that's what we've had in both of the previous examples. We had a function that we were trying to hit 0 with, or an equation that we were trying to hit 0 with. And the other thing is we're not given a starting guess here. So that means that we're actually going to have to create both of those things ourselves. So I'm going to go ahead and start here by just trying to understand how I can get a function here to be equal to 0. Like how can I see that as the goal of this question? So first I'll start that note that if the cosine of x is supposed to be equal to x, then what we really would want to happen here, or alternatively we could say that we want the cosine of x minus x to be equal to 0. So now we actually do want something to spit out the value of 0. And so we could now go ahead and say, how about we create now a function f of x, which is the cosine of x minus x, and now we're curious when this function will equal 0. That's perfect, because that's exactly what Newton's method can help us do. Newton's method helps us find roots of functions. And so we've changed the starting question into a question that we could then change into saying that a function needs to be equal to 0. So now I can go ahead and state that the derivative of this function is, let's see, it's going to be negative sine of x minus 1. So this is my derivative. Well, now I'm going to need to make a starting guess. I have the function and I have its derivative that I'm going to use with Newton's method, but I need to make an initial guess. So we need to make an initial guess. Now, there are plenty of initial guesses that we can make. In fact, there's not necessarily a right or a wrong initial guess. I mean, there are probably better and worse ones. Like, let's just think about a couple quick things here. We know that the cosine function can only spit out answers. The output of this, whatever it is, we know is only going to be between -1 and +1, right? That's the only thing that the cosine could ever produce. So if I was looking for a value of x that makes the cosine equal to this value of x, let's see, what would happen if I plugged in a number, say, like 1,000? I know that the cosine of 1,000 is only going to produce a value somewhere from -1 to 1. And a number from -1 to 1, is that even close to equaling 1,000? Well, no. So this might be a bad starting guess. It's not that it may never work, but it just isn't a great call. I want to pick something that almost makes these two sides equal already. Okay, well, you could probably come up with a lot of values. What if I plugged in the value of 0? Cosine of 0 would be 1. And does 1 equal 0? No, but I'm not looking for them to be equal yet. I'm just looking for these things to be close. So maybe I could do a starting value of 0. That seems pretty reasonable. I could do something like a starting value of 1. I don't exactly know what the cosine of 1 is, but I know it's somewhere from -1 to 1. In fact, if I think about my unit circle, I know that if 0 radians is right here, and pi over 2 radians would be an angle going up top, and pi over 2 is about 1.57, then the cosine of 1 would be a value somewhere around here, meaning that it would get me a value, I don't know, maybe around like a half or a 0.6 or something. So maybe I could say that the cosine of 1 is pretty close to the value of 1. Seems pretty reasonable. So there are tons of values that I could go ahead and pick. And again, there's no right or wrong value to pick at the start. There are probably just better and worse values. I'm going to go ahead and actually just say, how about we suppose what's going to happen if we start with that value of x equals 1? So how about we state x1, our first guess is going to be 1. We think if we plug 1 in here, our answers are going to be pretty close. Now again, I don't know how many approximations I'm going to need here because I'm not told to do 3 or 4 or 5. I'm told to make sure that the first 6 decimal places are accurate. So to do this, I'm going to go ahead and actually use my calculator to help me figure out how to find my next approximation very, very quickly. And to do that, I'm going to follow those steps that are going to be in the box here. So let's take a look at how I would do this. First, I'll clear off the screen so I don't have anything else on there. And then I'm going to type in my initial guess value, which in our case is the value of 1. And then I'm going to click this store button right here. It's right next to 1. It puts in this little arrow. Now I always like to store this over the value of a. So notice I hit alpha and then the math button. That brings up the green letter A there. What this means is now anytime I do a calculation where I involve the value of a, the calculator is always going to think that a is 1. So just notice a couple quick things here. If I did say a times 9, that should be 1 times 9. And so the calculator tells me 9. If I do a minus 1, the calculator should tell me 0. So the calculator thinks a is the number 1. So again, I'm doing 1, and I'm going to store it to this value of a. Now once that's done, I can go to my calculator and start typing in that formula that calculates my next approximation. But I'm going to do this using a's. So I'm going to do a minus, and now I have to set up a fraction. So I'm going to set up some parentheses. So on the top of this fraction, I'm going to have to plug my value of a into the original function. So notice that would be cosine of a. Let me move back over there. And then minus a. Notice that's what my function looks like if I plug a in. Then I'm going to divide by the derivative of my function. So I'm going to do a negative sine of a minus 1. Right? This is what I have. Now, I don't hit enter yet. If I do hit enter, this will show me what the value of x2 is, my next approximation. And while that's great, what I'd like to do is to set up the calculator to recompute this line again automatically. And so here's what I'm going to do. At the end of this line, before I hit enter, I'm going to click the store button again, and I'm going to say a. What I'm telling the calculator to do is to use the value of 1 in this calculation, and then save that new value, save whatever x2 is as the new value of a. So when I hit enter, I get this value. And the calculator now thinks, instead of a being 1, a has been updated to this value. So I'm going to go back and actually write this value down. I'm going to write down the first 6 places of it, since that's how many places I want. I'm going to get 0.750364. That's my next best guess as to what makes these two sides actually come out equal. Well, now I'm going to go to a third approximation. I can tell here that if my first guess was 1 and my next guess is this, nothing about my first guess was good enough to keep. All of it kind of changed. But let's take a look here at x number 3. How would we calculate this? Well, back on the calculator, what I essentially want to do is rerun this entire line. Now that the calculator thinks a is this value, I want to do this value of like the 0.75 minus the cosine of the 0.75 minus the 0.75 over the derivative with the 0.75 plugged in. I want to do all of that. But the calculator will always rerun the last line that you typed if you just hit enter again. So notice when I hit enter for the next time, it's going to run through this calculation, assuming that the value of a is 0.7503638678. It's going to think it's that value. And then it's going to create this new value, and it's going to immediately save that as the new value of a. So I'm going to go ahead and I'm going to write this value down. This is 0.739133. Now something interesting happened here. Apparently, something in my guess number 2 was good enough to keep. Notice the 0 was good, the point was good, and the 7 was good. I kind of feel pretty confident now that my answer is 0.7 something. But since everything else has changed, I probably should keep going here. Nothing else was good enough to keep from the previous line, so I might need to iterate on this again and improve. So again, all I would do is I would go back to my calculator, I hit enter. The calculator is again going to rerun the previous line with my new value and spit out another value. Okay, so now I'm going to go ahead and I'm going to write this value down. So this is going to be 0.739085. Oops, that's the wrong screen. So let's see, I'm going to do this value here. This is 0.739085. Okay, great. So I can look at this and kind of go, ooh, good. Some things are kind of being kept constant from the last time through. So now I feel really confident in this value. All right, but I need to get all 6 values kind of locked in. So I'm just going to keep doing as many approximations as I need until I get this. So back to the calculator one more time, and I hit enter. I'm going to now write down what this value is. And you'll notice 1, 2, 3, 4, 5, 6, all the way up to this 5, the calculator produced the exact same values. So now that all of those values have kind of almost been locked in, I'm going to say that I estimate that x would be roughly 0.739085. Let's go ahead and actually see if this works. Notice again, I could go to my calculator and I could go to the cosine function and actually see if I typed in this value. Notice I need to make sure I'm in radian mode, but if I type in this value, do I actually generate this same value back? Does cosine of x actually equal x? And you'll see, not exactly, because there's this extra 223 here, but holy crap, that's really close. That's awesome. This is working out beautifully, and I'm getting a lot of accuracy very, very quickly here. So this is the idea of using Newton's method with the calculator.